Okay, thank you all. Just going to give a brief introduction. Tonight we have our annual Einhorn lecture. The Einhorn lecture is underwritten and sponsored by Steve Einhorn and Sherry Einhorn. They are graduates. Steve Einhorn is a graduate of our school. He also endowed the Einhorn studio that Brian and his team designed. And he and his family also endowed the Einhorn Walk, the pathway that goes from East to West Campus that used to be Campus Drive. So I'm just going to give a very brief introduction, and Zhenfei Wang is going to give a more formal introduction to the speaker. We're very lucky and very excited to have our speakers tonight. They are a young office, although they've built quite a lot already. They're Beijing-based. I somehow know them from almost 15 years ago. All things from the Netherlands. They even attended some of my classes in Holland. So it's very strange. The world is very small. I'm really looking forward to their lecture. They have published pretty widely in China and elsewhere, but in particular in China. And so they also, you may know, are doing, in addition to the lecture tonight, they're doing a workshop this week, and which will conclude on Friday. We're also, they will also do a lecture in New York City on Saturday at the Fisher Center, and if this lecture is not enough for you and you really want to see them again, then I invite you to go at 4 p.m. on Saturday and see them at the Fisher Center. So I'm not going to introduce them. I'm going to let Fei Wang do that. I'll introduce now Fei Wang, the assistant professor and also coordinator for the Masters of Science program, and he will give a more formal introduction.
Hello. Welcome to Einhorn lecture by HHDFUN, and it's my honor to introduce them since we all share the same last name. And also people sometimes confuse me with him because our name is very, very familiar if you know Chinese. So HHDFUN is founded in Beijing 10 years ago. It's one of the leading offices in China. For me, they are the best among all the architecture offices under 40 years old. And in terms of their quality and quantity of their build work and prototype experimentation and systematic research and design methodology. Then they invited me over the summer to write a long introductory essay for their 10-year retrospective and monograph, which will be published by Tianjin University Press later this year. And in return, they have to come to Syracuse to give a lecture, and then a lecture in the Fisher Center, and also a 4-day-long workshop. And HSB is interested in the integration of knowledge from various fields outside architecture and applying it to architecture design, working collaboratively with artists, fashion designers, mathematicians, engineers, and others. They enjoy producing unexpected designs that go beyond the conventional. The firm explores new design possibilities by means of crossover cooperation. Luming and Zhenfei have won numerous design awards, including winners twice, 2015, 2017 Iconic Award in Germany, 2016 German Design Award, A Design Award in Italy, Grand Architecture Creation Award in China, WIN World Interiors News Awards in UK, and the new Chinese Architecture Award sponsored by Architecture Studio Office in France and Area Magazine in Italy. So they are very well known in Europe and not that much exposed in the US yet. And their work has expanded worldwide, including 3 times in Venice Biennale, twice in Architecture Biennale, and once in Art Biennale. And Shenzhen Architecture and Urbanism Biennale in 2017, this year. And both of them, they received ByArc degree from Tianjin University and advanced master degree of architecture from Berlage Institute in Rotterdam. They both worked at UNStudio, Amsterdam prior founding HHDFUN. And they are conducting a 4-day kind of a parametric workshop, and so the final review will be on Friday morning. So you're welcome to come to the VC studio to take a pic. And another tableau is that they never lectured together, and so it'll be the first time. So without further ado, please welcome HSB and I'm sure you will have a lot of fun. Fun is their real office name.
Okay. And thanks, Michael, and thanks, Fei, for the introduction and for having us here. It's our pleasure to talk in Syracuse, and thanks everyone for coming. Oftenly, we have been asked about what kind of architecture we do. And we always tried our best to explain to them in a very accurate way. We're not designing a building, we're designing a system. But most of them getting more confused after that, until we show them this project. 8 queens puzzle. It has nothing to do with architecture right now. Huh? The 8 queens puzzle is a problem of playing 8 queens, chess queens, on the 8x8 chessboard. But no 2 queens will threaten each other. That's a mathematical definition. Okay? And the solution requires no 2 queens share the same row, the same columns, or the same diagonal lines. It still has nothing to do with architecture design right now. But if you imagine you are asked to position 8 buildings in the 8x8 grid, but keep the best view of each building without blocking each other. This will be a solution, right? Because each row and each column and each diagonal lines, you have only one building. Then you will ask, there will be other parameters like the traffic, like the sunlight parameters you need to position the building. Then let's see how many solutions we have. We have 92 solutions for the 8 queens puzzle problem. This is the tower. So you can choose from the 92 solutions by adding other parameters to choose the best way of positioning your building. Okay, so people understand. Okay, you are doing parametric design. Then they get more confused again when they saw this project. This is an installation project. So do you feel a little bit strange when you see this photo? Because in order to take this photo, you have to stand right in front of the mirror, facing the mirror to take this photo, right? But you don't see yourself in the mirror. It's actually by slightly folding the mirror, your image, your reflection image about this mirror will be here, and about this mirror will be here. So you will be not visible as the position you stand, right? So then people get confused about it doesn't have the appearance of parametric design.
So as you can see from these 2 projects we had, our work is not really focused on the appearance of the design, but it's really the logic behind it. During our thesis design project in the Berlage Institute in 2007, we found designing a system is far more fascinating for us than designing a building. It is more dynamic than what we used to have. So we're very excited to see that one system could generate countless variations. From 2007, we started to do research on systems. We need to do research on systems which has not only a form generator, but also flexible enough to accommodate different site conditions, different user groups, different programs, etc. This pie chart, this pie chart it's a work in progress diagram, which shows our interested systems on the outside, and on the inside. So in the inside, it represents actually one project that consists of all different aspects in this pie chart. So if we overlap all of them together, this is another one and another one. So if we overlap all of them together, we'll have an infographic of all the projects and research we have done for 10 years. We start to show a very simple example of it's called Finsler. It's basically a geometric principle which could generate associative geometry. So you have two squares that attach one another on one point. And then from these two middle point and these two center point, you connect these 4 points together, you're gonna get another square. So this is a diagram we did for a T-table. We have two squares on the bottom, and this middle square, it's in the middle. And if we lift it up, and we can generate countlessly from this square to this square, and this one to this one. All the in-between profiles are all squares.
Okay, so this is the design. The reason why it looks like that, because this is a design for activation. We will ask to design an installation by using 2x2 wood sticks. So then that's the reason why we cut it in this way. And the principle she was talking about allowed us to make a very simple design, but very interesting, because there was no money and no time for this project. This image is the construction drawing for the table. And this is the construction process. Very simple. Just put them together, then we have the table. We were always trying in our office, we were always trying to operate in a very low, relatively low construction, relatively low technical construction situation in China. But we always keep the high technology design process. So this is one of the examples. And if you look at this image, by lifting this square up, then you actually create a three-dimensional structure with these V columns and with the roof. So by using this principle, we designed a temporary pavilion for a Chinese brand called JNBY in this big hall in Beijing. This is the installation, this is the pavilion they were used. So the squares on the ground, they connect to each other. It generates the squares on the top. And these structures, these V columns, are the lines from the series. So by adding no element for the mathematical theorem. And this HP surface actually make this structure more stable. And that's the process how this one was generated step by step. Lift it up, and you put them together, you will see the squares on the ground which generate the squares on top. The whole installation took 18 hours from scratch to complete it, because one night of the rental cost 80,000 RMB for the rental. It was too expensive. So it has to be very fast and looks nice. Yeah. Because of the flexibility of this system, so it's very easy to manipulate this whole system, which allows us to actually design this whole space. But that was a geometrical system, and then we applied the geometrical system on site to accommodate all the functionalities. For example, we have a main stage, so we have a big square here. We have a runway here, so we have a longer space, column free. And then we have some place for exhibition. We have an entrance should be perpendicular to the glass, something like that. So this is the exhibition space, and that's the runway, and that's the stage. The fashion show was happening, and that's the whole thing. Okay, ByArcs.
Okay. ByArcs. ByArcs is a curve composed of two circular arcs such that they connect with a matching tangent. It is a lot of application in the game industry, such as producing a sword trace or a road generation. But in architecture field, it has been used to simplify complex curves. It's called ByArc fitting. So if you can see, this is the basic principle of the ByArc. You have two vectors, the red one and the blue one, and they will generate two arcs in between, and it's tension here. So in the curve fitting process, you're going to have a free-formed three-dimensional curve, and then it will be simplified into different parts of circles. So all the red parts, it's a circle. All the blue parts is another circle. All the point in between is their tension point. And this is all the situations when the vector is different. The curve it generates will be different too. And even with two identical vectors, it will have countless variation of the curves.
This is a project we did in 2008. It's actually the second project we did after we came back from the Netherlands to China and opened our office. A very small pavilion. We had this design. We had this design first. Then we found this is the machine, whichever possible we can use. The machine can only produce arc in a very traditional way. Then we have to simplify this geometry to arcs. That's where the ByArc came to us at the first time. But it was very successful. They produced it in 3 days and assembled on site in 2.5 hours. Yeah, we sit here watching them. And yeah, it was very quick. And after this, in 2010, we designed the exhibition space, also in Shanghai, but in a larger scale, with the same principle, the same team, the same machine, in 20 days. The ByArc, also the small bending machine. Also the furniture and the exhibition, yeah. And in 2012, we just keep enlarging the scale because this is just a principle. So in 2012, we designed a bridge using the same principle. Then this time the machine doesn't work, so they have larger machine which can only make arcs. The arcs works everywhere. In industry, in building industry, right? Yeah, only arcs works actually. Yeah, yeah. But then we start thinking, can we do it smarter? Can we not every time make a curve and simplify the curve to arc? Can we just do something by arcs? So then we got the chance in 2015 in Tianjin University for a workshop. It was a 9-day workshop that we were asked to do 3D bending at that workshop. So we were thinking about, okay, let's do the ByArc thing. So the ByArc actually, as Luming said, the two vectors can generate very, very special curves. It looks very fancy, but all of them contains only arcs. This is the principle we used for our workshop in Syracuse. So you can see the result on Friday. So with the students, we designed a lot of variations here, but only change the vectors and the curves. In the end, we choose this one, because we were asked to do also urban furniture for the workshop if possible. So we designed one component and we position them and connect them together. We made a laser cutting model. The laser cutting can only do flat things. So the arc is actually flat geometry. So you can see this joint. This is the joint where the two arcs meet each other. And again, this is the machine, just a little bit bigger, the 3-axis machine. 6 years after the first one, the same machine, same technique. It's always happening. Yeah. shit happening. You know? So this is the machine we actually, together with the worker, produced the installation. That's all flat band metal tubes. Okay, so we transport them, easy to transport them back to the studio, and we just assemble them together to this bench. So these are the students. That's 2 elements, heavy metal stuff, 4 of them putting together. We did all of this within 9 days, including the design, fabrication, and also everything. Okay? So the students were quite happy. That was the exhibition in Tianjin University. So all of them are arcs.
So then the next is actually not it's not a geometrical principle, it's more an algorithm. So it's called L system. L system is a rewriting system, and it's used to describe the behavior of plant cells to model the growth process of plant development. It's basically just in the biological field to use it to stimulate the plant growth process, as you can see here. It actually can create a real complex system. So we have more ambitious with L system to use it more complex, but we had our first try as an installation that we going to use one of the features from L system, which is its rewriting system, which means if you can see this diagram here, that this part is actually self-similar to this one and it's self-similar to this one because it's rewriting itself. So all the joints actually are identical.
Which is very important. You know, you can imagine, it's a very complex system. It's a very complex installation, 15 meters high and very, very big. And all these joints are identical. Identical joints can solve all the production problems. So this principle allowed us to do huge scale project, but very simple. And this installation took them only 1 month, including prefabrication for everything. And this is the way how they install the thing on site. So you can see it's a large scale thing, but very fast. And cheap.
So, okay. So circle packing. Circle packing is another algorithm. Circle packing is actually a study of arrangement of circles, either variable or equal on the given surface, and will be no overlapping on each other, and they will all touch each other on just one tension point, like this. So there are actually 2 different ways of circle packing. One is based on a recursion algorithm, which we will explain later. The other is based on it's called perfect circle packing. The following 2 projects actually will use these 2 different algorithms respectively. The reason why we choose circle packing is also because it's very easy to manufacture and easy to locate on site. So it's still a low-tech choice in the Chinese construction situation.
Low-tech is very important. With the low-tech, you can produce a lot, very cheap and very fast, and with all kinds of clients. So, yeah, perfect circle packing. Perfect circle packing means every three circles will tension with each other. Only every 3 circles. Exercise. Geometrical exercise, a T-table. So by extrude all the circles with the same volume. So all the cylinders have the same volume. So you got the bigger circle with thinner plate, and with the small circle, longer, it becomes the leg of this table. So this is just a geometrical practice, a T-table by accident. That's another one. This is normal circle packing. It's not perfect, So you will find 4 circles or more than 4 circles just tangent with each other. But this is the recursive, not recursive. It's a recursive. It's a recursive algorithm. The interesting point about this installation is that it's made by bamboo. It's made by bamboo. It's very cheap and light material. Because of the tension point, the circle packing, right? Because of the tension point, there will be one point. The circle will touch each other. So this point will become the point where you connect them together easily just by wire. Okay? So it's very, very easily fast built. And then by supporting only several points of the whole installation, you will support the whole roof structure. And the shape of it's not flat. It's designed, it's supposed to be flat, but the material actually makes it not flat and not perfect circle anymore, but who cares? It doesn't matter, it just looks beautiful. So that's look from above. No circles anymore, actually. But it's supposed to have circles. Yeah. Then we just put this installation on the roof terrace, and it makes a beautiful party space. People just sit here and drink and talk with some light, solar light. Okay, and that's also an exhibition project. We did a lot of exhibition projects. That's in 2013 in Beijing. It happened in a very big industrial tank, which is circular. So the circular dimension of the tank, shape of the tank suggests the circle packing principle. We had a very big exhibition. This is 3,000 square meter space for the exhibition. We had 4 sub-exhibitions happening. So for example, this 6 identical circle was, we invited 6 Pritzker winner, like Zaha did, to be there. So each one has 1 circle. So they have to be identical. No one can be bigger. And we have also here the design competition exhibition, the student exhibition. We have 1 big circle is for the art performance during the opening. And all the other space, our circulation space, also we put some installations here. So then we make the perfect circle packing. This time it's perfect circle packing. Every 3 circles were put together. The perfect circle packing has one very interesting feature. As long as you position 2 of them, and then the third one, the dimension of the third one is fixed, then you don't need to measure anymore. Just put it, because there is only one position which can fit. So theoretically, you don't need to position every point during the construction. You can start from here with 2, and then you can just put one by one, and then it will be constructed. But that's theoretically. So then, these are the exhibition space, and all the others, the small circles, were the lightings. These small circles are lifted above. So for the lighting, for all the exhibition lighting situation, people always like to stay in the dark space and look at the brighter exhibition board, right? So that's why we designed the lighting like that. We designed it just along the circle, just light up the exhibition board, but no lighting in the middle of the circle. So these lights make the board light. And the circulation space needs some light because people need to be lighter. And also the installation needs some light. So you see all the small circles were lifted up with this lighting system, and all the big ones, they are just displayed. Yeah. That's the art performance in a very big circle during the opening ceremony. And the reason why we do this incline, the board arrangement, is that we want to give people freedom to choose if they want to look at the whole 3,000 square meter space just by look this way, or they want to look down for the exhibition content. That's the big space, the whole space. That's the ceiling. Okay.
So a recursive process. Okay, I'm gonna read it, but it's actually from Wikipedia. I don't know.
It doesn't really matter.
How well explained. A recursive process is one as one in which objects are defined in terms of other objects of the same type. Using some sort of a recurrence relation, the entire class of objects can be built up from few initial values and a small number of rules. Anyway, but let's just give you two very famous examples. This is a very famous, almost the most famous example of recursive geometry. It's a Fibonacci series. And this is a fractal. It repeats itself and in different scales. So these two are actually all based on recursive algorithms. We did a project in Shanghai that is based on a recursive program. So actually, you can see all the triangles. This triangle is, you find the middle point and you lift it up and then you subdivide it and you subdivide another one and then it's a recursive process. This is a project, this is actually an installation that we work with an artist to create a on-site installation of one of his 10 virtual installations. So it's also, the whole art project is a recursive concept. Oh, you don't have the inside, okay.
Yeah, I did the inside because it's not
Sorry.
recursive. But the recursive process basically is just repeating itself once again and again. So it produces triangles in different scale, and one of them becomes the entrance of the installation. Okay. This is a shop. It's a shop located in Shanghai, in Xintiandi area. If you go there, you can find the shop. The shop this is the product sold in the shop. It's a food product. It's very small. It's like this. It's very small. Because they have only this product to sell, so the shop needs a very, very strong identity for the product. Since Shanghai actually has the colonial culture, so we thought it might be interesting to combine this. And we found this light. It's very interesting light. This is a recursive geometry. You see, it's getting smaller and smaller and smaller. It's a recursive geometry, but an Art Deco light. So we thought maybe we can start from this point. And we start to research on the fractal recursive hexagon. Okay. That's a door handle. So this is the plan of the shop. We basically use the recursive algorithm to generate a fractal pattern. It's a fractal pattern which accommodates all the functions of the shop. For example, this is a big table here. The entrance is here. We have a pattern there, and that's a display table, and also the bar area. Everything together. Yeah, that's the shop. So you see here, this is a display standing, and that's a big table. The big table is a display table, but sometimes they have some events. They invite people to come to taste their food, so then they become an event space, something like that. And if you look at the top, since the product is here, the product is very small, so we design something very strongly, which is recursively getting smaller to attract people's attention. Yeah, that's from exterior. That's the bar area, and that's a big display area. This shop is one of the interesting aspects of the shop. It combines the cutting-edge technology like the 3D printing and 3D milling together with the handcraft, traditional handcraft. This one is handcraft, but 3D print first. I will explain it later. The bar area. It's made by brass. Hand polished. Also, the floor is handmade. Okay, so this is the door handle. In order to make this, we need to 3D print it first, and then we mold it and make a steel one, and cut and make it brass again. So it's the door handle. 3D printing. The sealing, we use the CNC milling machine and then make the molding. And brass is hand polished. This is the pattern on the floor. It's handwork to make all these small joints. This is 5 millimeters thick. Yeah. And molding. And this display table, first 3D print the shape and then hammered by hand every piece of them and then weld them together and polish it. So basically we used all the techniques including the cutting edge things and also the hand making or the traditional way. Tensegrity. Okay. Tensegrity is very interesting. Actually, it's a structure principle. The tensegrity is a system. You have a tension element and compression element, but no bending inside in the system. The reason we put it in the recursive algorithm is that after the research, we found actually by recursively replace one of the tension elements, for example here, the tension element, by a group of tension and compression elements, you will generate more complex tensegrity form. It works step by step. So it starts from a very simple one, and by replace one and replace again and again, you have a more complex form. So this principle allows you to start from very simple starting point, then you get more and more complex. Then this is a lighting. It is a light installation we did in the park. We make 3 of them, a group of them, which by the tensegrity principle and by the recursive algorithm. And made by Bamboo, it's a lighting festival, so it has to be a light, but it actually has nothing to do with light. Yeah. Yeah. HP surface, okay.
HB surface, it's a doubly ruled surface. It contains 2 families of mutually skewed lines. The only 3 doubly ruled surfaces are pure plane and HP surface and single sheeted hyperboloid, which means the double curved surface is made by 2 series of straight lines, and their intersection point is very easy to be calculated. So this property makes it easy to realize with concrete and explains its frequent use in modern architecture. So this is a diagram about a project that we did with HP surface, and this is a plan. And then if you have a plan, and then you lift it to this 2 corner, and then you get this, and then you split it by half, and then you have another one put together. So basically, we have a 3 HP surface put together as a prototype. And you can see like this. Because of its all straight line features and their easily calculated intersections, so all the structure and substructure, everything in the ceiling, they can all be very easily located. So if we manipulate it in different ways, we get all different kinds of variations.
5 components together.
So this is the rendering we have. And this is a structure drawing with all the weak columns.
Yeah, because if you look at this is one prototype, the 3 elements together. And this point is this point. It's a supporting point. And the V column is actually the edge of the HP surface. So by putting these 3 HP surfaces together, you get not only the surface, but actually the structure together. Yeah, so this is a very pure system. But if you look at here, yeah, structurally, in order to connect them together, so you have to split on top. This is a technical issue. Interior rendering, see the straight lines and the V columns. Under construction, V columns and very big column-free space. And these are the space frame structure with the HP surface. This guy. Yeah. We also designed something smaller. This is a font. It's basically a font that we designed also by the HP surface, also but cut it to life. It just looks nice. Nothing special. Okay.
No. It's actually, this is a research actually inspired by Free Alto and Shower. They did a research on structuring of space and unplanned settlement, and their form finding experiments in self-generated structure. The relationship between the occupation and its connection is the key of this research. So we were inspired by that, and we did also some research on the grid, either the grid system or the N-arm junction model. And it's evaluated by its number of neighbors and its accessibility and its road efficiency, etc. So we had actually a couple of projects. It's based on this research. Okay, so this is a grid model that this is one of the grid model that we did. It's a very simple one.
Diamond grid.
Yeah, it's a diamond grid.
grid.
It's a very simple one, but it's easily to be deformed. So we had a project. Actually, we have two projects beside each other. So we tried actually using two different models. This one is the diamond grid model, and the other one is based on the N-arm model.
The reason why we use diamond model, not triangle, because the diamond model can be manipulated three-dimensionally. It can shift point up and down, so it works three-dimensionally. And this is not a flat site, so we manipulate the whole diamond grid to make this model. And it's a service center. It's located in Qingdao in China. It's for 2014 Horticulture Expo. It's a service center for the expo. Yeah, 2 years from design to construction complete. It's here. This is the whole master plan. The building is all located here, and we have another project here, which is another service center. We built two service centers here, and this is the main pavilion of the expo designed by UNStudio. So that's the site. Nothing special, but some big trees. So we just kept the big trees, nothing special. And we just, of course, we limited the amount of soil which need to be taken shift. Okay, so here comes the diamond grid. The diamond grid basically solved architecture together with the landscape. And for each diamond grid, we have three elements. The green one in the middle is basically grass, water, landscape. And the light gray one is the circulation. Will work there, the circulation. And the dark gray one will be the staircase. So for every diamond grid component, we have these three elements. And then we apply them everywhere. Then you see the variation here. The green, landscape, and here is water. It was dry when I took photos. And the circulation space here. Then the staircase. The staircase sometimes it becomes just a seating area. It sometimes becomes just a roof element, and sometimes it becomes real staircase. And also can be flat. When it's flat, it's just a planar. So basically, by variation, it generates different function within this field. Okay, so it's a continuous field with the same similar principle. Yeah. Because the building located in the mountain area, so it has to go very well together with nature. So you don't see the building actually when you stand on top of that, but you will see all these big trees which was kept during the design. And this building has Sunken Plaza, which was here. So now we're standing on the Sunken Plaza. These are the shops. These are the shops, a restaurant for the service center. And then these are the trees which were added. And that's the Sunken Plaza on the corner of the street. Yeah. And that's the landscape, the staircase, the sitting area connecting the landscape and building. Yeah. That's the typical weather in China. You know, no clear skies. Yeah, but anyway. Okay, next one. This is the second service center I was talking about, the one I was talking just here, and this one is here, and this is the main pavilion designed by UNStudio. So they were on the main axis of the whole Horticulture Expo. As you can see, this one also located in the middle of the lake, and we kept all this island. We just add more trees, and we made the building. It's actually a quite interesting system, I think. It's a 3-arm junction. It's a 3-arm junction here. But normal 3-arm junction will have just one center point. But by shift this center point, we will generate a triangle in the middle, which can be controlled by the circle in the triangle. So this is a very flexible system. You can change the direction of this 3-arm. You can change the dimension of the circle, which generates a grid or a routing system. The interesting point is here, the different dimension of this different joint will connect to different degree of activities. We will have this kind of joint. It's only for traffic, because no space left. We will have small space, then people can stand there and talk. We will have larger space, then people can meet there. So in the field, in the very complex field, you need different dimensions of the joint to accommodate different programs. So basically, we arranged by this system different dimension and shape of this joint system. And also, as a service center, it has to be very easily reached. People have to come here very easily. So this system has to connect with the surrounding road. So this 3-arm junction system is very flexible because it's an open and closed system. The closed system, it can generate closed routing, which will be the surround routing system of the building. And it also can generate open system, which will connect to the surrounding. So basically, this feature already have the building made. That's the closed system, that's the open system, that's the variation of the 3-arm junction system. Can you read it? Yeah? Yeah. Okay. Closer. Then we start design the building according to the program. This is a wheel analysis. You have the best wheel here with the water and here with the mountain, whatever. Then we position the restaurant here on the second floor, and because of the original site situation, we just put the other restaurant here on the ground floor, which connect the water more closely, and we kept all this existing island, put more trees there. Yeah, and these are the arms which connect to the surrounding. Yeah, then we generate all the roof terrace and all the staircase and others. Okay, that's the look from the island. You don't see the architecture at all. Those are the trees we add. And from the lake side, that's the building. So the building goes very well with nature. And that shows the building, the roof terrace of the building connect to the main road of the expo. Yeah. That was taken from one arm. That's the amphitheater facing the water, the lake, and that's the restaurant. This is the restaurant. Yeah, and different variation of the stair system, lighting system. Yeah, very simple. Okay, let's get back to the small scale. We do big and small, no scale difference. That's an installation. That's an art installation we did for an art project on the roof terrace. The interesting thing is here is the joint. This is actually a binary tree somehow topologically it's a binary tree. It's three-armed, always three-armed junction everywhere. The three-armed junction, if it's a tension structure, then the joint will be flat. It will be flat. Otherwise, it will be stretched to be flat. So, since it's flat, it's very easy to make the joint, right? Then the whole thing becomes very fast and very cheap. That's the thing before tension. And that's the drawing we gave them. That's the way how they work on site, actually. Yeah. It took, I think, half day, less than half day to install the whole installation. And basically no money. Yeah, that's the result. We were quite happy because it was very cheap, very fast, and produced very interesting effect. And also it has some structure feature. So after that, we got the chance to renovate a building. This is a factory building. We renovate this building. At the same time, we actually make the design for this whole plaza. So we thought it might be a very interesting experimental thing to make a larger scale of this tension system. So we make this time a larger scale. It's 100 meters long. This time with steel cable. And since the surrounding is very complex, we build up 12 walls, concrete walls, and then we connect all the concrete walls together with the building by this system. That's the topological tree of this system. Since the plaza needs lighting as well, so this system becomes the lighting system of the plaza. Because of the feature of this system, it's calculated in kangaroo. It's a tension structure. So the position of the lights, they are quite even, which generate very nice lighting situation. Yeah, you see the light system, and these are the points which connect to the wall from above. That's the skating park. This is the big structure system. And the joint, again, the joint is very easy to make because the whole installation took 4 days to install without supervision from the architect on site. I was only calling from Beijing. The project was in South China. So, but they made no mistake. They made no mistake. It was interesting. That's somehow the system connect to the building and connect to the roof of the building. Yeah, those are just neighbors. They just come to play. See the lighting situation. It's quite good. And we also make light. Yeah. This installation at the same time a lighting situation. Of course, it's a very active place right now. People come to play with bicycle. They just come big event, and they play with skating board. And people come every day, and yeah, and people come for photo shooting for the fashion designers for Chinese brand. This is the brand, and also they come for a fashion show. So it becomes very fashion space in Xiamen. Yeah, Voronoi.
So actually, Voronoi is an algorithm that I think is probably the most used algorithm in the architecture field,
used.
Especially in students' work. You have seen it thousands of times, and it will be used by generating all different kinds of organic cell structure and all that. But actually, if you really think of Voronoi is a diagram. It's partitioning of a plate into regions based on the distance to points in a specific subset of plan, which means the set of the points, all these red points, it's called seed. For each seed, there is a corresponding region. In the blue one is the region, and the red one is the seed. They're all in this blue region, all the point is closer to this seed rather than to any other ones. So actually, if you really think, what is the feature of Voronoi? This is one of the features of Voronoi. If you think the application of it, we think that's probably a nice thing to do a roof structure of it. Because if you think the rainwater comes from above, and then in this piece of roof, all the water comes to this downpipe. And in this piece of the roof, all the water comes to this downpipe. It's a very efficient roof structure for collecting rainwater. So this is not our model. This is actually a model redone by other students, but it's based on FreeAuto's very original model. It's a standard model. It actually explains what I have just said, the features of Voronoi. So it's actually, you make a box of sand, and then you have a certain hose, and then you unplug all the holes. The sand will itself form this structure. So we have a project in a very rural area in northern China, and it's on a hillside. It's very short of water, so we've been asked to do a very small project. So we thought, why not just do a roof structure which can collect water in a Voronoi way. So this is the village. There you go.
Okay. The last project. Sorry. So we have several projects in this village. The plaza, one coffee and book restaurant, bookshop, and one hotel. Let's talk about this one first. It's a reading center and a cafe. Original situation was like that. That's the courtyard we need to renovate. So one thing she was talking about already, the water collection, if possible, will be the best. And then the second thing will be, of course, the trees. We have to keep the trees, otherwise people will kill us. So then we just measured all the trees. One good thing about Voronoi, the Voronoi was generated by points, right? So we just put the position of the trees here, and we add our water collecting system here. So those points, huh? So together, we generate the whole courtyard. And the courtyard was the position of the courtyard has the water connection system at the same time kept all the trees. It's supposed to be like that. And then you see the drainage here. The water comes down from here, from this downpipe here, and then it goes to the drainage system, and the system will go away to a bigger pipes. The very low technology construction in rural area. But they did it very good because they are familiar with this construction methodology. So that's the completion of everything. But yeah, one thing is a pity. They don't have enough money right now to formulate the whole water collection system. So right now it's a shading device, but we have already the downpipe and all the drainage and everything done. When they have money, we will just put here something to collect the water. So it can be changed later. And at the same time, you see all the trees. Not even one tree was cut during the construction period. So it was just kept. This is the image when all the renovation was finished. The whole building was turned down and built up again. So you see all the trees are kept, and the water system is here. And that's the interior. It's a bookshop and a coffee shop. People come here just to play. And this is the guy who helped us build this courtyard. This is the very first coffee in his life he had. And then they have many other events also in this space. For example, this is a shoes exhibition for a 90 years old lady in this village. And they come to just enjoy the space. Children come and they just enjoy the movie and also come to the library to read. That's another project. It's a small hotel. The same thing, we have the trees here. We don't have the water collection system this time, but we have the trees here. So we'll apply again this principle, and we generated this courtyard, kept the trees. It was winter, interior. Yeah, toilet. With wheel. Shower with wheel. On the back side, because those two toilets, those are new toilets we add for the hotel, also generated by the Voronoi algorithm. And on the back side, we have a hot spring, which is here. For the same algorithm, because there were many trees here. So it was generated the same way, 3 pots and many trees. And this is me. Yeah, I was there just together with all the farmers. I just told them how to make the egg stone. That's how they make it. They test if it's comfortable. Yeah, so that's the hot spring. And this is the plaza. The coffee was here. The coffee shop was here. So you see the trees and all this water collection system, and that's the plaza here. So the plaza needs lighting again. So we use the same principle as we used before, but this time there is a different, because we have only several points surround the plaza where we can connect our tension system. So it changed to a closed system with only several points connection. So this system together with the previous one actually can somehow solve all the similar situations already. Yeah, this is how they build it. That's the lighting. 3 days work of construction. The life goes on. Yeah, that's how they use the plaza. Okay, thank you very much.
Thank you. Any questions?
Thanks for sharing us those excellent cases. And in my past experience, those computer generation may be with some mechanical sense. So my question is, can you do a quick introduce about how you balance the mechanical sense of computer generations and the organic form that design requires?
Sorry. The question again? How to balance what?
How you balance those mechanical sense of the computer generations and the organic form that the original design required.
Mechanical and
Mechanical and organic.
Organic.
Yeah.
Is this
Do
a
you
problem?
think our project looks organic?
Or mechanic?
Cause sometimes the mechanical sense will make the design or maybe the product feels like not alive, but the organic things will looks like more natural.
Okay, so do you know how organic thing was generated?
It's come from the nature.
It comes from the nature, but by rules.
Yes.
Okay, so you have a principle first. Then you play with the principle, you generate the organic form. Okay, so there is no difference if you use mechanical or just organic. Organic has nothing to do with mechanical. Okay, the organic is just generated by principle. So if you have right principle, for example, you play with complex theory. If you play with more flexible algorithm, you won't generate organic things anyway. So I don't think it's a problem. I don't know if I answer, but I think it's a problem. It's just if you choose the right principle to do your design.
Hello.
Yeah.
Thank you for sharing such incredible projects. And personally, I'm your fan in China when I was an undergraduate.
Yeah.
And my question is, how you can decide how you can decide the algorithms, because the system or the algorithms is you have each one in each project.
Yeah.
So that for me, maybe in one project, I can use L system, or I can also use Voronoi, but how you can decide which one I want to use?
Okay.
Or it's all come from the nature, or you have other relationship with the project itself?
Okay. You want to answer?
Well, I think actually we said a lot of words of unexpected or unconventional and all that. But actually, in the design process, that we still concerned as a conventional architect, you still have problems to solve. And you still have to consider every aspect in all conventional designer will do. So actually, the answer to your question is we have a sort of as you can see the pie chart, a pool of a system, and we consider all the aspects. Sometimes we make different options as well, and we try to find the best one to fit the situation, or either solve the problem or more fit to the surroundings. So it's actually, the same.
So, but just to follow up on that question,
That's
so
right, yeah.
does the pie chart drive towards an algorithm, or is an algorithm a part of the pie chart?
The pie chart actually consists many algorithms and the geometrical principle. Because this question I will take for every lecture I give. Yeah, so it's a very popular question, how you decide, right? But it's the same question if you're just a conventional architect, how you decide your design, right? You have to solve the problem. You have to make a good design. But the interesting thing is, since we have the pie chart, we have the tool pool, the library. So every time we will try different options from the principle. But with your experience, of course, you will first choose some of them. The experience, not blindly choose, right? You will choose some of them. For example, the circular of the tank, the shape of the tank already suggests something with circle, right? Square doesn't fit. So it's basically a trying thing. But I think most of the case, after several try, you already get an idea if the tool you have in the pocket can solve this project or not. If not, then you're not lucky this time. Then you have to search for something else. But if you're not lucky at all, then this time maybe you cannot use this methodology. It happened. It happened. So not every project can be used for all this principle and solve problem very nicely. Yeah. So, but basically, I think this is something. It's not a problem. It's not a problem. All the project you saw here is around 8-9 years of research and study and the work we did. So when you go further, if you look at pie chart, there are some area which was actually still black, right? Nothing there. So basically, we did research there, but we have no project there right now. But what we want to do for the next 10 years, maybe to fill it up a little bit more with all the principle. But what I will give you a suggestion is that during your study and your daily routine work, you can look for principles without purpose. Okay, just look at the book. Just save every interesting principle in your pocket. Then when the day comes, you meet some project. Then you will have something in the pocket. Then they meet. Okay, the Fensler came like that. Okay, everything actually came like that. Okay.
More questions?
I could just make an observation about that, about the last point you made, because in the big landscape project you showed, of course, the Benjamin Berkel UNStudio Caroline Boss project is the back.
Right.
And in fact, what's happening with the pie chart is very much like what UNStudio does with what they call design models.
Right.
And present the projects is what you show are techniques, let's say singular techniques, either algorithms or simple geometrical principles that then lead to the project. And then each of those actually produces a result. But what you never really say, which to me is the most interesting thing, is that each of those results fit back into the pie chart, right?
Right.
So, in a way, you've done something much more complicated and much more interesting than you've described, which is you, in 10 years, have generated a kind of knowledge-based system that's represented in the pie chart, each project of which is producing a piece of this knowledge. And so what you said in the end is, yeah, you can approach a project now with the solution in the pocket, right?
Right.
It's not really a solution. It's the way you've solved it in the past, and it's represented on the pie chart.
Yeah.
My assumption is each of the solutions lets you evolve and make the last solution more rich and more complicated. So if I were talking about your work, I would constantly refer back and forth between the larger pie chart, which is basically like design models, and how each project is derived from an algorithm or a natural geometrical formation, and how each of those solves it and then adds to this. Because I think, I think what you've done or what you're doing, I think the model of the practice it's incredible. I think it's really remarkable. For me, it's much more compelling and much more interesting than simply showing a beautiful project or than showing a software or that. I think it's a very big system that you really have to be clever to get inside of. But once you get inside of it, I agree with the student down there that I'm a huge fan, but maybe for that reason and not simply for the solutions. I think the system that you created, coupled with the techniques and with the beautiful projects, in my view, is really remarkable, really incredible work. So I want to thank you for presenting it.
Yeah, I have a lot to say about their projects, about them, because it took me 4 months to finish the article for their new book. But in one sense, I mean, it's very contradictory. They are conventional architects. They build buildings. On the other hand, they are unconventional architects as well. They do all the experimentations. That's why I said just in terms of the prototyping, they are pretty amazing. And also, they, in just 4 p.m., they got interviewed by our student magazine, Posit, and they were asked, so how do you think about to give any advice to our students for the future to do our practice, to have their office? And they said, be prepared. Although you see their projects really, really cool, but they are also architects. They have to persuade the clients to get it built. Rather than they get a pretty form, they just automatically there. It's not possible. And also, their system, also they said they are not interested in the result. Everything you have seen there, they are not interested. They are more interested in the process, how to generate those, then persuade the clients, then get it built. Of course, they have to do they only show a small part of it, of all their portfolio. So, of course, they did so many prototypings already. They tested, they fail, or they're successful by different materials, not just form. We are trained, we can design pretty forms. Can you build it? And that's why they are building the workshop is you have to build one-to-one kind of scale installation. And even the same form, try different materials. So that's why they are so remarkable. Think about them. They are not 40 years old. And so, they've been having their office for 10 years, how many projects they have built. Think about that right now. When you are 40, how many projects you can build. So, okay, I hope everyone...
But this is what drives me crazy about it. Because that big project you showed, right? I can tell you there are 50 architects, I'm 58 years old, who are my age, who would spend 2 hours telling everybody here about every detail of that project. Why? Because that would be the biggest and most important project of their life.
Yeah, you don't know how
And
many.
what makes me crazy about you is that you told that project, you showed that project like, yeah, whatever, we just did this. It's like, what are you doing? You need to hire me to talk to people, sell them on these projects because they're absolutely. I think that project is absolutely.
Yeah, of course they haven't told you. So for all the single projects, how many top star architects they have bidden to win all this kind of projects.
They don't
So
care.
they are just 30 something. So they will have a really, really bright future. Also, I hope everyone had fun tonight. So actually, the last thing I'm going to mention is actually FUN is their office name is Formation Unlimited Network. So that's their office name. So nobody asked that. What does it mean? I said so many times, FUN. Okay. Thank you, everyone.
Okay, thanks everyone.